this lesson, we are going to use properties of exponents to evaluate and simplify expressions involving powers. We are going to put numbers into scientific notation and back into standard form, and we are going to use exponents and scientific notation to solve real-life applications. First, let's begin by reviewing some of our power rules. So if we have like bases and we are multiplying them together, please remember that what we need to do is to keep the base and we need to add the exponents together, m plus n. For example, if I have 2 to the 3rd power times 2 to the 4th power, that's going to be 2 to the 7th power. Our quotient power, we're going to keep the base and we're going to subtract the exponents. So for example, if I were to have 3 to the 7th divided by 3 to the 2nd power, that's going to be 3 to the 5th power, subtracting the exponents. Remember to keep the base. When we have the power to a power rule, we're going to keep the base and we're going to multiply the exponents together. For example, if I have 2 to the 3rd power and I'm raising that to the 2nd power, I multiply the exponents and that's going to be 2 to the 6th power. If you recall our zero exponent rule, any number to the 0 power is 1, but the base cannot equal 0. With negative exponents, we want to make sure that all exponents are positive. So if you recall, we simply take the reciprocal and that makes our exponent positive. The power of a product and power of a quotient rule just remind us that each part of the term needs to be taken to that power or exponent. So if I had ab to the m power, that's going to be a to the m power and b to the m power. If I have a quotient that is to a power, I simply have to remember that everything in the numerator needs to go to that power, as well as everything in the denominator needs to go to that power. Let's do some practice examples. If I have x to the 4th times x to the 2nd, remember that we keep the base and we add the exponents. For those of us that want to remember what this means, if I have x to the 4th power, that means I have 4 x's times x to the 2nd, which is 2 x's. So altogether I have 6 x's, and that's why the shortcut rule works. If I have x to the 3rd raised to the 2nd, and that's the power to a power rule, I'm going to keep the base and I'm going to multiply the exponents together to get x to the 6th. What this really means is x to the 3rd power, and we want 2 of those. And if I were to expand that even more, I would have 3 x's and 3 x's. And that is the shortcut rule then, is to multiply those together. When I have a product taken to a power, I recall that each of the pieces needs to be to that power, and it's by multiplication. Remembering it's 3 to the 1st power and x to the 1st power. So each of the parts of the term need to be taken to that power. So it's going to be 3 to the 2nd power and x to the 2nd power. 3 to the 2nd power is 9, and I will have my x squared. In the next example, we have a quotient, so we're going to keep the base and we're going to subtract the exponents, which would be x to the 3rd. If you would like to see that in expanded form, remember that in the numerator we would have 5 x's, and in the denominator we'd have 2 of them. We can simplify one numerator and one denominator, which leaves us with 3 x's in the numerator, which is x to the 3rd. In number 5, remember that any number divided by itself is 1. This is an example also then of the zero rule, that I would subtract the exponents. That gives me x to the 0 power and shows that that's 1. In the next example, you can subtract the exponents and we would get x to the negative 2, and when we flip that over to take the reciprocal, it would be 1 over x squared. Or another way to think about it, that there would be 3 x's in the numerator and 5 x's in the denominator. And when we would simplify, Most of the x's were in the denominator, that's where my base will go, and 2 of them would be left with a 1 in the numerator, 1 over x squared. Evaluating each expression, I have 3 to the 4th power raised to the 2nd power. Simple terms, I'm going to multiply the exponents together, which is 3 to the 8th. And then using your calculator, we need to simplify that expression. It comes out to be 6,561 using your exponent key on your calculator. In the next, we have a quotient raised to a power. We need to make sure that the numerator is raised to that power as well as the denominator is raised to that power. And then we need to make sure to simplify. 5 to the 3rd power is 125, and 8 to the 3rd power is 512. In the next example, we're going to keep the base, which is -2, and since we are multiplying like bases, we are going to add the exponents. -3 plus 9 would be 6. Now we want to simplify, taking -2 to the 6th power, and that will be 64. Let's do a couple of more examples. So we have our quotient and we are taking that to the 3rd power. There's a couple of ways we could accomplish that. One of the ways would be to simply do a power to a power, which means we would multiply. So I have a to the 6th and I have b to the -9. But please remember that our final answer needs to be all positive exponents. Since the b to the -9 is in the denominator, we're going to take the reciprocal and that will move it up to the numerator. So we have a to the 6th and b to the 9th. Another way to work out that problem would be to take care of what's inside the parentheses first, a to the 2nd, and then we're going to move the b to the numerator right away, which is b to the 3rd, and then we would raise that to the 3rd power. So we would come up with the same answer of a to the 6th and b to the 9th. In the next example, we're going to keep the base, which is -y squared to the 5th. So this really means -1. So -1 to the 5th power is going to be -1. Y to the 2nd raised to the 5th would be y to the 10th. And then we have a y squared, and we have a y to the -12. Now, when I combine like terms, I'm going to keep the base, which is my y, and I'm going to add the exponents together. 10 plus 2 is 12, plus -12 would be 0, and I still have my -1 out front. Any number to the 0 power is 1, and 1 times -1 would be -1. In the next example, I'm going to simplify first. But remember, these problems can be done in more than one way. So I'm going to bring the exponent of a 3 into each part of this expression. So this r has an exponent of 1 times 3 would be r to the 3rd. And then I have s to the -3 power. So to simplify, I'm going to move the s's to the numerator. So I have an s squared and an s to the 3rd in the numerator. And I have an r and an r cubed in the denominator. If I simplify, I would have 1 r taken away from the numerator and 1 from the denominator, leaving me with r squared. Then I need to finish by combining like terms in the numerator. The product of s squared and s to the 3rd, I keep the base and I add the exponents. There would be 5 s's, and I would have an r squared in the denominator. In the next example, I'm going to bring my exponent of 3 into each of the parts of this expression. Power to a power, I'm going to multiply. Please remember that the exponent attached to the b is a 1. So I have a to the 6th, b to the 3rd, and then I have a to the -3 and b to the 15th. Now what I need to do is to take the reciprocal of the a to the -3rd to make it a positive exponent, which means I'm going to move it to the numerator. So when I bring the a to the 3rd to the top and I have an a to the 6th already there, that's going to be a to the 9th. When I take care of the b's, I have b to the third in the numerator and b to the 15th in the denominator. So I'm going to keep the b in the denominator, and I would have 12 left. So I have a to the 9th over b to the 12th. In the next example, I want you to take a look and remember that scientific notation uses exponents to write numbers in a more compact way. So we recall that the form of scientific notation would be our number times 10 to a power that describes how many decimal places we would have, where the c is a number that is greater than or equal to 1 but must be less than 10. And n, the exponent, is an integer. When we write a number in scientific notation, what we want to do is to move the decimal, so we're creating that number between 1 and 10. Then we add our base, which is 10, and our power. We've moved the decimal 12 places, but because this exponent gives us a direction on how to get our number back to standard form, our exponent would be, we've moved it 12 places, but we want to move it 12 to the left to get back to our original number. So our exponent will be negative 12. For letter B, we're going to move our decimal between the 1 and the 3 to give us 1.39 times 10. I moved the decimal from the end 9 places, and because the 9 is going to describe that I want to move my decimal to the right 9 places to get back to my original number, it will be positive. Letter C, I'm going to move the decimal between the 3 and the 0. I am moving my decimal 6 places, and it's going to be a positive 6 because that would tell a person putting this back into standard form that I would need to move the decimal 6 places to the right to get back to my original number. In this example, I'm going to move the decimal between the 9 and the 4, and I've moved the decimal 4 places. But in order to take the decimal and move it back to its original number, it would need to go to the left 4 places, and that is why my exponent will be to the negative 4. Now we'll use this in a practical application of scientific notation. The red blood cells, white blood cells, and platelets found in human blood are all generated from the same stem cells. In laboratory experiments, scientists have found that as few as 10 stem cells can grow into this very large number, 1,200,000,000,000,000,000 platelets. I'd like to take that number and I would like to put this into scientific notation. That's going to be 1.2 times 10 to the 12th power. The number of white blood cells generated was 1/40th the number of platelets. I'd like to take 1/40th and put that into decimal form, which is 0.025. And then I'd like to write that into scientific notation, which is going to be 2.5 times 10 to the negative 2 power. I'm going to multiply those two together to find out how many white blood cells were generated. When I do this, I'm simply going to use the commutative property, which means I can multiply in any order. So I'm going to multiply these two numbers together. 1.2 times 2.5, which is 3.0. Then I'm going to keep my base, and I'm going to add the exponents together. 12 plus negative 2 would be 10. And that tells me how many white blood cells I would need. Or, if you would like to write that out, that will be 30 billion white blood cells. To review, remember your exponent rules, that if you are multiplying, you're going to keep the base and add the exponents. If we are dividing and we have like bases, we're going to keep the base and subtract the exponents. If we have a power raised to a power, we're going to keep the base and multiply the exponents. Remember, if you have a negative exponent, we simply take the reciprocal, which makes the exponent positive. Any number to the 0 power is 1, as long as that number is not 0 to begin with. If we have a power that we are taking to a product, we're going to make sure that each part of that product is then taken to that power. And if we have a quotient, we will do the same, where we will do the power to the numerator as well as the power to the denominator. Please remember that scientific notation is written in the form c times 10 to the nth, where c is a number greater than or equal to 1 but less than 10, and n is an integer. Please complete the reflection.